Welcome, everyone. I'm really excited about introducing this new robotics course. For people who don't know me, my name is Li Fengzhou, and I'm a new assistant professor in the department. I will be teaching this course, Decision Making for Robotics, this coming fall. In this course, you will learn about the principles of decision making in robotics. This is different from the motion planning problems, where robots need to figure out how to go from point A to point B. Well, in decision-making problems, we will design higher-level algorithms that decide what points A and B should be, depending on the task at hand. For example, as shown in the videos on the right, these underwater vehicles need to decide where to go to optimize their joint searching performance. Similarly, these drones need to decide which actions to take for tracking targets like animals on the ground. Also, most scenarios require making sequential decisions where the output is a series of goal locations or actions or tasks. And the decisions the robots made in the past may influence the options available in the future. In the first part of the course, I will be covering several specific research topics. I will start with the information strategical planning. You will learn about what submodularity is and how to optimize a submodular function. Submodularity typically happens in the case where the contributions of the robots may have some overlaps, like the coverage overlap. And then their joint contribution becomes a submodular function. Leveraging submodularity, you will learn how to design approximation algorithms for multi-robot task assignment and for multi-target tracking. And when the robots are operating in unknown environments, there will be some uncertainty associated with their performance. So I will be talking about chance constraint optimization and risk-aware planning to managing the risk induced from the uncertainty for the robots. Also, the robots may perform tasks in environments where they must plan strategically to counter adversaries. So for this, I will cover some adversarial planning techniques like a minimax search and Monte Carlo tree search to make sequential decisions for the robots to play against their opponents. So in the end, I will teach you about how to use reinforcement learning to learn policies for the robots to optimize its long-term reward, and how to use graph neural networks to design decentralized learning architecture where each robot communicates with neighbors only to make decisions. In the second part of the course, you will present a research paper in the class and submit the reviews for one other research paper. I will provide a list of papers relevant to these topics, and you can choose any two from it. Also, I would like to emphasize that this is a research-oriented course, and an ideal outcome of this course is a research paper that can be submitted to a top-tier robotics venue. For the research project, you will work in groups, and your project can be one of the 3 tabs. So one option is to do an in-depth survey of a research area related to these topics. Second, you can work on formulating a new research problem or solving an existing research problem. So it's perfectly okay if you cannot solve the problem entirely during the class, but you must demonstrate sufficient effort and progress. Or you can implement an existing or new algorithm. This can be entirely in software or on hardware. There are no explicit prerequisites. It would be helpful if you are familiar with the areas such as probability and estimation, algorithms, machine learning and AI, optimization, and robotics, but this is not required. The only requirement is the ability to read and critique research papers. But I will also talk about how to review a research paper in class. Also, there's no required textbook. I will provide with you the lecture slides and the corresponding tutorials. Okay, I think that's it. If anyone has any questions, feel free to reach out to me. Thank you.